good morning, good evening, good afternoon, depending on where you are. I think we'll get started now. All right, well, thank you all for taking the time to join us. My name is Anaïs Ferraud. I'm the SE4D Managing Director, and I'll be your host today. Before I introduce the speaker and we get started, I'd like to take just a moment to share a quick announcement. We just opened the applications to the registrations, to host an early career as part of our exchange program. This is our fourth and final edition of the exchange program. So if you are a scientist based in the US or in Chile and you are interested in welcoming to your group for about a month, a student or a postdoc, please visit the link in the chat that I'll be posting in a couple minutes. And applications for participants will open on July 1, so stay tuned. Quick housekeeping now. This webinar is being recorded and will be posted later on our YouTube channel, where you can find all of our past webinars. Live translated captions are available. You can select your preferred language by clicking on the closed captions button located at the bottom of your screen. We also have a Q&A feature that you should feel free to use, also available at the bottom of your screen to ask all your questions to the speaker, and we'll get to them at the end of the presentation. All right, so now I'm very happy to introduce today's speaker. Ikuko, welcome.
Thank you.
Ikuko Wada is an associate professor at the University of Minnesota, Twin Cities. Ikuko's research focuses on the geodynamics of subduction zones and the physical processes controlling earthquakes, mantle flow, and arc volcanism. Ikuko combines numerical modeling with geophysical, geochemical, and laboratory data to better understand the complex dynamics of subduction systems. Today, Ikuko will be talking about thermal deformation and hydration evolution of the Forearc Mantle Wedge corner. Ikuko, please take it away.
All right. Thank you, Anais. Well, thank you so much for the invitation to give this webinar. So I decided to take this as an opportunity for me to synthesize some of the work that our lab has been working on under this NSF CAREER award that I received several years ago. And a lot of work that I'm presenting today was conducted primarily by graduate students Lindsay Kenyon, Jeremiah McElwee, and Vivian Sharma. So as the title suggests, the focus of this study has been on Forearc Mantle Wedge corner. But I just want to step back and say that the mantle wedge in subduction zones do host important processes, including serpentinization, impacting water cycle, melt generation for arc volcanism at the surface. It also interacts with megathrust earthquakes and episodic tremor and slip events. Earthquakes in the subducting slab and overriding mantle could also be influenced by the rheology of this mantle wedge corner as well. The mantle wedge as well, so in general. Now, again, the part that I'm focused on is the Forearc Mantle Wedge corner here, which is generally imaged or inferred to be cold and stagnant. And this is because this part of the mantle wedge is decoupled from the subducting slab, resulting in relatively low surface heat flow at the surface. Now, this is in contrast to the down dip part of the mantle wedge where the mantle and the slab are coupled, inducing this mantle wedge flow that brings in hot mantle into this region, allowing melting to happen and arc volcanism. Now, modeling work and geophysical observations indicate that this slab and mantle decoupling tends to be extend to about 70 to 80 kilometer depths for most mature subduction zones. I use mature to indicate that the systems that are more or less in steady state. Sorry, I see one. Oh, never mind. Oops. So the focus of this study is this cold stagnant mantle wedge corner. If we do add water to the system, we can form serpentinites. Now, the serpentinization reduces the strength and the density of the mantle. It also increases the volume, and so these changes in physical properties can impact deformation, buoyancy, and also permeability as well. So the overarching question that we want to address is what controls the extent and degree of serpentinization in the wedge corner, again, because it can impact processes surrounding this area. Now, serpentinization requires fluid, and the degree of an extent of serpentinization can be constrained from geophysical observation. So this is an example based on VP variations in the mantle wedge corner, plotted against the thermal parameters of the subducting slab. So in many subduction zones, the forearc mantle wedge corner seems to be about 20 to 40% serpentinized. Now, thermopetrologic models predict that the serpentinization or high degree of serpentinization may be difficult if we consider how much water is being released directly beneath the mantle wedge corner. So this is showing in color, the warm color is indicating where we have sufficient water being released, again, directly beneath the mantle wedge corner to cause high degree of serpentinization, which can happen, is predicted in Cascadia, Nankai, and Mexico. But elsewhere, the amount of water being released beneath the forearc wedge corner is relatively low. Now, is the serpentinization controlled by the fluid availability? Well, it can be, but it can also be that the fluid can migrate from deeper depths to the shallower depths, such that it's not just limited, the fluid source is not limited directly underneath. So I'm just going to quickly and briefly talk about how fluid migration can happen along the subduction interface or within the subducting slab up dip, such that we can have fluid source from deeper region. So this is a model by Wilson et al. The white arrows indicating fluid migration pattern along the interface. This is within a high permeability channel. Again, deeper slab-derived fluids are being brought to the shallower depths. And this model on the right-hand side is showing the fluid migration within the subducting slab. So the lower panel is showing fluid source distribution, where the fluids are being released. So here we have antigloride dehydration happening, and then this is chloride dehydration happening. And if we have this type of fluid source distribution, the models predict that the fluids can migrate along these dehydration fronts up dip from deeper depths to a shallower depths, and potentially providing fluid source for mantle wedge serpentinization. So we do need to keep in mind that the fluid source may not be just the fluid being released directly beneath the mantle wedge corner, can be from greater depths. So today's presentation, again, I would like to present the synthesis of a few different projects that I worked on, or we worked on under NSF CAREER project. So I'll present thermo-mechanical models and also crystal preferred orientation modeling results to understand the thermal and flow evolution and its impact on shear wave splitting observations that have sometimes been used to infer serpentinization. I'll also present hydraulic chemical mechanical modeling for fracture evolution within the mantle wedge or during serpentinization. And this can impact how hydration or serpentinization can propagate within the mantle wedge corner. Now, this fracture evolution and propagation of serpentinization can also depend on stress state. So I'll present the results from earthquake focal mechanism inversion that helps to quantify the stress orientations as well as lithospheric deformation modeling for stress distribution in the overriding plate. So shear wave splitting has been used to infer mantle deformation previously when shear waves travel through an isotropic medium. They split into two orthogonal components, one being faster than the other, and the delay time between them, and as well as the direction of fast polarization, so the polarization direction of the fast component can tell us about the anisotropic medium that the waves travel through. Based on these shear wave splitting parameters, we can infer the crystal preferred orientation. So this is just an example for olivine. Olivine is an anisotropic medium. Depending on the orientation, the shear wave splitting parameters can also vary. So this is indicating, depending on the shear wave propagation direction, the fast axis of the mineral aggregates of olivine can change, and also the shear wave anisotropy also varies depending on the direction of its propagation. Oops. So then based on the crystal preferred orientation that we can infer from shear wave splitting, mantle flow or deformation has been inferred. So this is based on the experimental results that indicate how crystals would orient relative to the shearing direction. So in Forearc mantle wedge corner, many of them, or at least in Forearc regions, the observations indicate trench parallel fast directions. So for example, in Northeast Japan, we have trench parallel fast direction in the Forearc region, and then the fast direction transitions to trench normal in the back-arc region. And so there have been different mechanisms that have been invoked to explain this trench parallel fast direction, including serpentinization as well. So one question would be, can shear wave splitting tell us about serpentinization in the wedge corner? So to address this, the approach that we are taking is actually in the opposite direction from this observations to inferences. We actually calculate the mantle deformation condition and then compute what the crystal preferred orientation should be, and then also calculate shear wave splitting to see the impact of mineral CPO on shear wave splitting. So just jumping right into the thermo-mechanical modeling. So this is to compute the thermal evolution and as well as deformation history of the mantle in the mantle wedge corner. This particular model, it's a time-dependent model, and this is 1 million into the simulation. I am assuming both overriding and subducting plate to be relatively quite young, 2 million year old and 5 million year old. And I will talk about the impact of slab age or plate age in a bit. But with the young plates, the mantle at shallow depths is quite warm, and so it can flow quite easily as the slab subducts. This dashed line is indicating a prescribed slab surface. Now, 10 million into the simulation, the slab has subducted farther down. The conductive cooling by the subducting slab results in stronger mantle wedge corner, which causes stagnation, and therefore the maximum depth of decoupling deepens as subduction continues. So with this, the stagnant wedge corner expands with time. And then this red uh, zone is indicating antigorite stability zone. So if we are to add water, we can form antigorite here. Um, Now, one of the key thing is that antigorite can form only after mantle wedge corner becomes stagnant. So not while the mantle is participating in this mantle wedge flow. So that again, antigorite can form in stagnant, non-deforming mantle wedge corner. Now, older plates will result in cooler condition in the mantle wedge corner, which results in faster stagnation of wedge corner. So the stagnant wedge corner grows faster in the older plates. So then we use the strain history that we can obtain from these some mechanical models in the calculation of crystal preferred orientation and shear wave splitting calculations. Um, so here the crystal preferred orientation of mineral aggregates are being calculated at each node shown here on the right. And this is based on, again, the strain history that we obtained from time-dependent thermo-mechanical model. And once we have the CPO distribution calculated, we propagate a synthetic shear waves vertically. So this is with vertical incidence, and see what the shear wave splitting is. So calculating shear wave splitting parameters, which are fast direction and delay times. CPO is calculated using DREX, and shear wave splitting parameters are calculated using MSAT in our study. So this is going to show how the fast axis of mineral aggregates evolve through time. Now we have this blue line is a 1000-degree contour. Below this contour, the temperature is high enough that the mantle here is flowing, but above this shallower than this contour, the mantle is stagnant. Now these black bars are the fast axis orientations, and the lengths are the length is indicating the strength of the anisotropy. And initially, mineral orientations are minerals are randomly oriented. So as subduction continues, the system cools and the 1000-degree contours deepen. This part is still flowing and accumulating strain, and therefore CPO is developing. But at shallower depths, this part is no longer flowing, and therefore the CPO has been frozen in. Now, this is assuming A-type olivine CPO. And relatively, so these are, most of them are shorter, smaller than 5% anisotropy. So it is relatively small anisotropy that develops due to A-type olivine CPO that has been, again, frozen in this mantle wedge corner. If we do add water in this area, we can have antigorite forming. In the case of colder conditions, the anisotropy is actually even smaller or weaker because the mantle wedge corner becomes stagnant faster. So there is shorter time for the mantle wedge corner to develop CPO. So I'll talk about what happens when we allow antigorite to form in this stability zone in the next bit. But if we given this CPO distribution, again, if we calculate shear wave splitting, we end up having trench parallel fast direction, the surface, and then also delay time that is very small at the wedge corner and then increases gradually towards the arc. Now we do have some anisotropy here, but many of them are subvertically oriented, which does not actually give a lot of shear wave splitting. And that's why we have a delay time quite small. And then with the thickness increases, the delay time increases. Now, if we do add antigorite to this, or if antigrade forms in that condition, the mantle wedge corner is no longer deforming, and they form in a topotactic manner, meaning that the orientation of antigrade that replaces the olivine depends on the apparent olivine orientation. Um, so when we look at antigrade replacing this olivine, the fast directions these are the black bars on the sphere is indicating the fast axis for this antigrade. They are actually very similar to olivine. So the fast axis does not significantly, the orientation does not change significantly. Now, shear wave anisotropy strength actually is lower for topotactic antigrade. You can see that based on the color. You know, with olivine, you can have up to 16% or so anisotropy, but with antigrade, maybe 10% or so. So when antigrade forms topotactically, the anisotropy is not very strong. Now, if they do deform, antigrade deform, then the anisotropy can be stronger. But we do assume topotactic antigrade because of the stagnant condition. So when we incorporate that antigrade, topotactic antigrade in this in the mantle wedge corner, the fast direction actually does not change. Trench normal fast direction. Then this is because the fast axis do not change much going from olivine to topotactic antigrade. Now the delay time actually is predicted to be higher, significantly higher, but this is actually an overestimation due to simplification of this calculation. We are assuming that we have 100% olivine in the mantle wedge corner being replaced 100% by the antigrade. So it is significantly higher in delay time. It's more realistically, the delay time would be similar to or even smaller than what is predicted for A-type olivine. This is showing that the effect of antigrade or serpentinization in the mantle wedge corner on shear wave splitting is likely to be very small. And so, although serpentinization is sometimes invoked to explain shear wave splitting, but quantifying the degree of serpentinization from the observations is going to be quite challenging. Now, if we do use B-type olivine, fast direction is going to be trench parallel, which can explain the observations better in the Forearc region. But the delay time is going to be very similar or even smaller than predicted for A-type olivine. And then also, if we replace B-type olivine with topotactic antigrade, we can still get trench parallel fast direction, but the delay time trend, small value, and then actually increasing delay time towards the arc, this trend is not going to change. And these observations or these predictions cannot explain some of the observations that have been reported. So, for example, local shear wave splitting observations in Northeast Japan indicates trench parallel fast direction both onshore and offshore region of the Forearc. So here we have the cross section, and this is indicating trench parallel fast direction in the Forearc, and then trench normal fast direction in the back arc. And we also have relatively uniform delay time in the Forearc region and then increases towards the back arc. This particular pattern can be best described in terms of anisotropic overriding crust. So if we assume A-type olivine in the mantle wedge corner, and this can actually be also topotactic antigrade as well, but if this mantle wedge corner is overlain by an anisotropic crust, which has margin parallel fast direction, given the trench parallel normal faults present, then the shell wave splitting results indicate we have trench normal fast direction in the forearc region. Trench parallel fast direction in the forearc region and trench normal fast direction in the back arc. So there is this transition from trench parallel to trench normal by just having this anisotropic overriding crust. And then the delay time is uniformly low in the forearc region and then increase towards the back arc. So this really explains well the observations as Uchida et al. Also suggested. But in terms of mantle wedge serpentinization, the effect of its effect on seismic anisotropy is relatively small. So it's again difficult to decipher its impact from shell wave splitting. Now, we also want to know or better understand how serpentinization proceed within the mantle wedge corner. So this image is showing olivine being fractured and being replaced by antigrite and magnetite. This is a serpentinite exhumed from the mantle wedge in New Caledonia. And what we would like to understand is how this fracture evolves, because fractures provide um, pathways for fluid to migrate into the interior of the wedge corner and therefore serpentinization. Even if we have fluids available, if the fluids cannot propagate into the interior, we cannot have serpentinization. Now, this fracture process is likely to be impacted by stresses induced during reactions. Now, during serpentinization, the solid volume can increase by up to 50%. So with reaction, we have volume increase. The volume increase can result in clogging, but it can also stress the surrounding rock and cause fracturing. And so this is we are going to focus on the fracturing aspect of this or effect of volume increase. And once fractures form, the permeability increases and allowing fluid to flow and reaction further progressing. So this can lead to extensive serpentinization depending on fracture pattern. Now, the mantle wedge corner is part of the overriding lithosphere, and it is under tectonic stress. So in addition to this, what we call reaction-induced stress due to volume expansion, we also wanted to understand the impact of tectonic stress on fracture evolution. So this is something that Jeremiah McElwee has been working on. And we use a hydraulic, chemical, mechanical model, which consists of a number of discrete disks that are connected by elastic bonds. These bonds have certain strengths, so normal, shear, and torsion strengths and stiffness. Now, when the stress on them exceeds these strengths, then the bonds break and there will be crack forming between these disks. Now, when these disks hydrate, they become bigger. So this volume expansion again imposes stress on the surrounding disks, and when the stress exceeds their bond strengths, they break and form cracks. In addition to that, in addition to this reaction-induced stress, we wanted to see the effect of tectonic stress or background stress. So we vary the stress on the boundaries to simulate the effect of horizontal deviatoric tension, hydrostatic condition, and deviatoric compression by varying these sigma y and sigma x. We use relatively low effective confining pressure of 1 megapascal. Jeremiah is working on higher confining pressure models at the moment. but there is some trend in the impact of confining pressure, or that will be to be reported later. Pore fluid pressure controls how the fluid migrates. So we are assigning a lower fluid pressure in the interior such that the fluid migrate towards the uh, interior of the model. So the fluid is being introduced at the base of the model domain. Again, once the disks interact becomes hydrated, then it expands and causes stress variation. So this is the modeling results for deviatoric tension, hydrostatic, and deviatoric compression cases. Now, black lines are cracks that are connected to the fluid supplying channel. So that's where fluid is migrating and therefore hydration is happening. So this is where we have disks expanding, and that is stressing the rocks surrounding and then causing further fracture cracks. Now, red ones are isolated cracks, but they will eventually become connected to the fluid supplying channel, so it turns into black. Now, in the case of deviatoric tension, horizontal deviatoric tension and hydrostatic condition, these fractures can propagate into the interior of the model. And this type of fracture pattern we are calling branching fractures, where fractures form in a hierarchical manner and resulting in extensive hydration. Now, in the case of horizontal deviatoric compression, though, these branching fractures do not happen. Instead, cracks happen near the fluid supplying channel, causing localized hydration. So this is the pattern that we call a spalling fracture pattern. So depending on the background stress state, we actually have different fracture pattern. So now this is just showing the the change in fracture pattern with going from horizontal tension to horizontal compression. Now this is horizontal tension means it is the tension is parallel to the fluid channel. So the system is under tension parallel to the fluid supplying channel. And to the right, we have compression parallel to the fluid supplying channel. And this orientation is important. Now, in the case of horizontal tension, again, we have branching fractures, but as horizontal compression increases, spalling fracture dominates. So based on these results, what we can expect in terms of how serpentinization can progress in a certain environment varies with the tectonic stress or stress state. So in the case of mid-ocean ridge and outer rise, in outer rises, we have subvertical faults, generally normal faults that are under deviatoric tension, horizontal deviatoric tension. And so the fluid supplying channel is subvertical, and compression is parallel to that fluid supplying channel. And this is the case where we expect spalling to happen, where only localized hydration is likely to happen, not extensive hydration. So that's what we would expect based on the modeling results for mid-ocean ridge and outer rises. Now, for the mantle wedge corner, though, the state of stress can likely to vary depending on the subduction system. If it is under a compression, horizontal compression, then again, the hydration is likely to be limited along the subduction interface or the base of the mantle wedge corner. While if it's under horizontal tension, then we can have extensive hydration happening in the wedge corner. So can this explain the observations? Now, the question is, we don't know what the state of stress is in the mantle wedge corner. Now, the overriding plate, the stress state of the overriding plate depends strongly on how much plate coupling force is being applied, as well as gravitational pull force that's being applied on or acting on the margin slope. Um, and we, again, whether the mantle wedge corner is horizontal tension or compression, it can depends on these factors. Now, horizontal compression would mean that when the margin normal stress is greater than the vertical stress. So that would be the margin normal compression. And if that happens, the model predicts that the hydration is localized along the mantle wedge, the base of the mantle wedge. If the horizontal stress is smaller than the vertical stress, then we have horizontal tension, which can allow extensive hydration. So to constrain the stress state in the mantle wedge corner, or actually in the overriding plate, we use focal mechanism of earthquakes. So if we have earthquakes occurring in a particular region, and assuming that the stress state in that region is uniform, we can invert the compression and tension axis from the focal mechanism solution to obtain the stress orientations. So by inverting these P and T axes, we are trying to find out this stress state that can explain all these focal mechanisms. So this is just an example where the maximum, intermediate, and minimum principal stress axes are represented by red, green, and blue regions. Um, and so this inversion, focal mechanism inversion gives us the orientations of these principal stress axes and also the relative stress magnitude. Now, we can't actually constrain the absolute stress magnitude, but it can tell us how big they are relative to each other. So if we are looking at stress tensor in like a strain ellipsoid, we can actually determine the orientation and shape of the stress ellipsoid, but not the absolute size. So this is something that Vivian Sharma has worked on, and so I'm going to just show you a couple of examples that he has worked on. So this is from Northern Cascadia. We have these dots indicating earthquakes in the overriding plate. So these are cross sections. Pink ones are happening in the outer Forearc region, and when we invert the focal mechanisms, of these earthquakes, we obtain, or the inversion indicates that maximum stress axis, sigma 1, is more or less horizontal and normal to the margin. So this and vertical axis or sigma 3 is subvertical. So this is indicating that the vertical stress is smaller than the horizontal margin normal stress, and this is horizontal compression. So that is consistent with what we would generally expect for the outer Forearc region, where the effect of plate coupling is strong. But the inner Forearc, closer to the arc, the stress state can vary, and this is because of the competing effect of plate coupling and gravitational force on this margin topography. In region B, sigma 3 is more or less margin normal, horizontal, and we have sigma 2 being subvertical. So here we have horizontal stress smaller than the vertical stress and indicating tension. Now, if we go to C and D, we have sigma 2 being margin normal and sigma 3 being vertical. So these are actually indicating horizontal compression. So we have horizontal tension and horizontal compression. So along the margin, it varies. But more importantly, the R values for these results are high. And when we have high R value, it indicates that sigma 2 and sigma 3 that we are comparing, right? Vertical versus margin normal stress. These two values, the magnitude of these two stresses are similar. Okay, so it means that the stress state is more or less neutral, not strongly tension or not strongly compression. It's neutral. Now, in the case of Hikurangi, in the northern part, so that's the pink earthquakes, where pink earthquakes are happening, we have sigma 3 in margin normal horizontal orientation, which is smaller than the sigma 1 in vertical direction. So this is indicating margin normal tension. While in the southern part, with yellow earthquakes here, we have sigma 1 in subhorizontal margin normal direction, which is greater than the vertical stresses. And so this is compression. So we have horizontal tension in the north and horizontal compression in the south. So the stress state in the inner fork especially can vary depending on the subduction margins. And so we compiled these focal mechanism inversion results from what Vivian has done as well as previous studies. So this indicates that outer fork region is generally mostly horizontal compression, but inner fork again can vary from compression to neutral to tension, depending on the subduction margin. And there seems to be some correlation with the down dip extent of frictional coupling that controls the coupling force. Although there are some variabilities likely due to local, or I shouldn't say local, regional tectonic conditions. And also, of course, the strength of the fault impacts the plate coupling force as well as margin topography, which impacts the effect of gravitational force. So there's some variation, but there seems to be some correlation with the down dip extent of frictional coupling. So with this knowledge, we can actually see, can constrain the state of stress in the overriding plate, but primarily where these earthquakes are happening is in the crust. And what we want to constrain is the stress state in the mantle wedge corner. So to quantitatively assess the distribution of stresses in the mantle wedge corner, Vivian has been working on numerical lithospheric deformation modeling. So this is an example for Northern Cascadia. The model consists of elastic crust and elastic mantle wedge, and then viscoelastic asthenospheric portion of the mantle. And we apply shear stress based on the prescribed effective friction coefficient along the interface, and otherwise it is a free slip condition. And we vary the mantle wedge physical properties based on the assumed degree of serpentinization. So lower Young's modulus and lower density for higher serpentinization. So these are all for Cascadia with different parameterization. So this one has a friction coefficient of 0.03, and the plate coupling, frictional plate coupling is imposed down to 25-kilometer depths. The color is indicating the deviatoric stress. So with 50, actually the red is indicating horizontal compression, and then blue is indicating horizontal tension. And so with this parameterization and mantle wedge corner is not serpentinized, so it has a relatively strong mantle wedge corner. And with this, we have a compressional environment in the outer fork and neutral environment in the inner fork, stress state in the inner fork. The mantle wedge corner has relatively high horizontal compression, and this is because of the mantle is relatively strong. Now, this model doesn't consider the impact of a deformation as the subduction proceeds. So it is likely overestimating the strength of the mantle wedge corner, but nonetheless, if we assume elastic wedge corner with uh, elastic properties appropriate for mantle, we end up having higher stress in the mantle wedge corner. This would actually prevent extensive hydration in the mantle wedge corner. Now, if we do assume hydrated mantle, somehow if we get mantle wedge corner to be hydrated, so this is 100% serpentinization in the wedge corner and then gradually tapers down to 0 degrees. Then we actually have a weaker mantle wedge corner that leads to higher or greater deviatoric tension. So we have tension in the mantle wedge corner as well as in the overriding plate, overriding crust. If we increase slightly the friction coefficient and decrease the DOC, or DOC is the depths of down dip depths of coupling. So this is overall resulting in smaller plate coupling force, and therefore the forearc region is in less compression. Similarly, in the mantle wedge corner, it's in less compression. And if we have serpentinization in the mantle wedge corner, we have even greater tension happening in the mantle wedge corner as well as in the overriding crust. So there is an impact of serpentinization on the stress state in the mantle wedge corner as well as overriding plate. As serpentinization progress, it's possible that the change in stress state can actually promote even further serpentinization. So does tectonic stress control serpentinization? Now in Nankai, Cascadia, and Northeast Japan, the focal mechanism inversion indicate that the inner fork is under deviatoric tension, neutral, and compression respectively. And we also have observations that indicate some serpentinization in Nankai, extensive serpentinization in Cascadia, and little serpentinization in Northeast Japan. Can these be explained by tectonic stresses? And so far, the results indicate that there is some correlation where we have horizontal compression as indicate where in Northeast Japan with horizontal compression, the models indicate that even if there is fluid available, the hydration become localized along the base of the mantle wedge corner, and extensive hydration is difficult. While in neutral or tension stress regime, such as in Cascadia and Nankai, we can have fractures propagating into the interior, and therefore extensive hydration can be possible. So there have been a number of simplifications made in our study, and so this study, we are continuing to study this further, but at the moment there seems to be a good correlation between tectonic stress and the extent of serpentinization. So some of the key takeaway messages are mantle wedge corner initially is flowing during subduction initiation. So there is some strain, experiencing strain, but as system cools, it stagnates. And once it completely stagnates, then we can form serpentinites. Now, the effect of serpentinization on shell wave splitting is likely to be very small because of the formation of antigorite in a topotactic relationship with olivine. They do not have two different shell wave splitting features. When we have serpentinization, we have volume expansion, and that results in fracturing, but only when the fractures can propagate into the interior if the stress is tension parallel to the fluid supplying channel. So in the case of mantle wedge, if the stress is horizontal tension, we can have branching fractures that extensively hydrate the mantle wedge corner. Um, and based on the focal mechanism inversion results and mechanical molding results, there seems to be some correlation between tectonic stress and the extent of serpentinization in the mantle wedge corner. Thank you.
Thank you, Ikuko. If there's any question, please use the Q&A feature, or you can also raise your hand. Well, Ikuko, it looks like it was crystal clear.
Yeah, I only introduced each study briefly, but these most of the studies have been published. So if I'm sure there are lots of things that I didn't explain well, but I hope everyone people can look at those papers.
Do you have them on your website?
Ooh, I should update that. Yeah,
Oh,
but I have listed or cited those papers in my
in your
presentation.
in your
Yeah,
slides.
yeah.
Okay, Simon Peacock has a question, allowing to talk. There you go. Simon, go ahead.
Um, that was a fantastic talk,
Oh,
Goku. I feel like I've just been able to catch up on all your papers here in just 50 minutes. Um, the only question I have is just what are your thoughts about the relatively rare earthquakes that occur in the mantle wedge, in the Forearc Mantle Wedge? Are they telling us something about stress state, about fluid infiltration, or what?
yeah. So my answer is I'm not sure. I mean, certainly there are earthquakes in the Mantle Wedge corner in Northeast Japan, and I have also been looking at some anomalously deep supra-slab intermediate depths earthquakes in Colombia, for example, and they seem to be associated with certainly fluid. I want to say availability because when we look at the dehydration depths beneath those events, they tend to be associated with peak fluid release. Whether that is associated with serpentinization or not, I'm not quite sure. In terms of thermal condition, uh, I mean, certainly the temperature is low enough to cause that. But in terms of the mechanism of earthquakes, I'm not quite sure.
Okay, thank you. And again, excellent talk. Thanks.
Oh, thank you.
Thanks, Simon. We have now a question in the QA from Constanza Rodriguez Piqueda, sorry. Thanks for the very interesting talk. Maybe I missed it, but how does the maximum depth of decoupling MMD is constrained across the different subduction zones?
So MDD is constrained by surface heat flow and geophysical observations or seismic observations, such as seismic attenuation variation. We are basically trying to infer the thermal state from that. Because when maximum depth of decoupling sort of marks this transition from stagnant wedge to flowing mantle, where there's a sharp contrast in temperature, and that also results in transition in surface heat flow pattern as well. So it's a combination of thermal modeling and geophysical observations. And Again, they tend to be 70 to 80 kilometer depths, but there are certainly anomalous regions where it is shallower or deeper than that. But nonetheless, let's say if it's between 60 and 90, it's still unclear. It's still relatively in a narrow region, and what we don't know is exactly how this depth results in that depth range.
Thank you for your question, Constanza. We have time for a couple more questions. Giving some time for anyone to post their question or raise their hand. I am going to send the link in the chat that I promised I'll do, like the US and Chile exchange program. You'll have more information about this program and the link to the host registration platform. And a reminder that applications for exchange participants will open on July 1. And I hope that you will consider applying. All right, doesn't look like we have more questions, so I think it's time to thank our speaker. Oh, hang on, we have Omid has a question. Omid, you have the floor. Go ahead. Oh, hang on. Ask to unmute. You're muted.
Hello. It was a
Hi.
great talk. Thank you. And I have a quick question. What are the structural control along the strike or lateral fluid migration at a constant depth in the forearc? And how significantly does this lateral fluid routing impact variation in mantle wedge serpentinization parallel to the arc? I mean, how does this lateral fluid migration can change the serpentinization in the forearc mantle wedge corner?
Right. Yeah, we haven't studied along margin uh, fluid flow, but I would imagine that definitely it is likely to be happening. So, I mean, driven by pressure gradients as well as permeability structure or guided by permeability structure. Um, Even though so this that could be leading to localized fluid availability, but then in terms of serpentinization in the mantle wedge corner, again, even if the fluid is localized at the base of the wedge corner, if it cannot propagate into the interior, we can't have serpentinization. So again, I do think that the tectonic background tectonic stress can be quite important for that.
Thank you. Thank you. It was a great talk. Good
Thank you.
opportunity for me. Thank you.
Thanks, Omid, for your question. Well, looks like we are at the top of the hour, so now is the time to thank our speaker, Ikuko Wada. Thanks again so much for taking the time to present your work, and thanks everyone for joining us live for our EZ4D International webinar. As a reminder, the presentation it has been recorded and will be posted on our YouTube channel. All right, well, enjoy your day, everyone. Bye.
Bye.